So why is that? Because we know that if we take from the top over here, this is the distance we're going to find, which is going to call E, position of the centroid. So when you take from the top, you just do 50 plus E. When you take from the bottom, you have to remember to compensate. Okay, so the formula that we're going to use, so we know that this is the case that we have eccentric symmetrical loading. So we know that stress X is equal to Px over A. So this is straightforward. Then plus by Mz over Izz multiplied by Y. Okay. So I'm going to define our transformation by viewing this way. This is the X and this is the Y. This over here is rotation about the Z. Okay, so from this view, this will be my Y. This is my Z. This is rotation on the X. So if you were to ask me where is point A, B over here, so this is at the top, this is point A. At the bottom down here, this is point of at the bottom here, right? This is point D. Okay, or location on the plane of point D. Right. So Px is straightforward, right? Finding Px is easy. So Px from here, we know that Px is equal to 400 Newton. We don't know tensile compression yet. Later on, we'll analyze it. The thing is, Mz is equal to Px multiplied by 0.05 plus by what? E. You have to remember that you have to add the what? Plus by E. So the moment is taken up to the what? To the centroid. I repeat again, the moment is taken up to the centroid. Okay. So for this case, we know that the centroid and neutral axis is not at the same location. Okay. They're not in the same location, right? So from here, the first thing we're going to do, we're going to find the position of our centroid first. But before, yeah, let's find the position of centroid. Okay, but before we find the position of centroid, we know that the structure will deform this way, right? So if we look at the structure, I'm going to sketch out how this is going to deform. It's going to deform like this. Okay, that's how the structure will deform. Okay, so this is your deformation pattern. Excuse me, sorry. So that's our deformation pattern. So we know that it will be acting this way. This is our moment arrow. So this is going through compression. And this is going through tensile. Okay. Due to bending. Okay. So due to this is bending about the z-axis. Okay. And then if we are not sure whether the point. Okay. So we are going to draw half of it. Maybe. Right. So this section is our section of interest. So we know that we have a force going in as P, right? Action equal reaction. This will be your Px, right? So we know that the Px, now we know that this will be generated what? Tensile. Okay, it's hard to see down here. How to is it tensile compression? It's hard to see down there. Okay, so you take it. So if some of you, Eugene, what if I want to do the opposite side? Okay, if you want to look at the opposite side, right? So you want to look at the opposite side. So some of you want to analyze the other direction. So what you have over here. So now this is your P, right? And then this side is also actually correction, also PX. So either left or right side, you're going to get what? PX is inducing what? Tensile. I hope I clarified that, yeah? Okay. So the next thing that we're going to do, we're going to find the position of our location of our centroid. And I hope I did last week, like I did clarify that we call it centroid. We don't always call it neutral axis, okay? So from this view, so this is my y, z, rotation about x. I'm not going to do it. Okay, I mean I'm not going to do it. I'm not going to go into details into it, but I believe you all you know how to find your centroid. So this position over here is our centroid. Okay. So IZZ or the centroid which is y bar. This will be equal to 8.154 millimeters. Okay, 8.154 millimeters. So 8.154, as I said, the datum will be always taken from, for this case, I'll take the datum from the top. So this is equal to 8.154 millimeters. Okay. Then IZZ, YZZ, because this is along ZZ axis. And then if you were to do this, this will be your width. And then this direction over here, this will be a depth. So your IZZ will be 3.8802 times 10 to the power minus 9 meter 4. Okay. As I say, I'm not going to do this because I've done, if you look at last week, we have, or even the week before, okay, we have done enough of this and it's so repeating trend. I believe that you guys will know how to do this. And even though in our sharing stress, okay, we did second moment of area, so you guys should be really familiar with it. Then from here, the area of the entire structure, the cross-sectional area, will be equal to 104 times 10 to the power minus 6 meter 4. Okay, so this we calculate. Okay, so these are all calculated. Right, so we get centroid, IZZ, and area. Then now we're going to apply. Okay, we're going to apply what we're like. So the analysis, right? So if we're looking at our cross-section area, right, and knowing that we know the position of our centroid, right? So this is the position of our centroid. Right, and then based on our moment arrow, we know at the top we are going to have the top we're going to have what? So based on of our moment arrow, the top will be under tensile, the bottom will be going through compression. So from here, so let's find the position stress X about point A, right? So this will be equal to Px over A. So on top will be tensile plus by mz over izz multiplied by y, right? And based on transformation, these are y, z, rotation about x, right? So we know that px is equal to 400. Area we also know, right? So this will be equal to, and it's going to induce what? From analysis, it's going to be tensile plus by px is equal to 400 divided of our area is 104 times 10 to the power minus 6. And because at point A, the bending is going to induce in tensile, this will be positive. So mz, now mz you have to be careful, okay? So mz is equal to the force of 400. Okay, so it's going to be 400, right? Multiplied by the distance will be what? 50 millimeters, 0.05 plus by the centroid, which is 8.154 times 10 to the power minus 3. Okay, then multiply by y. So y over here is 8.154 times 10 to the power minus 3. Then divide by izz, which is 3.8802 times 10 to the power minus 9. So when you add this up, so 400, so it's equal to 3.846 plus by power minus 3 divided by 3.8802 power minus 9 is equal to 48.883 times 10 to the power 6, right? So at this point, it's going to be 52.527. Sorry, 52.729. Times 10 to the power 6 Pascal. Okay, and I'm going to put a positive sign so to show me that it's intention. And then the next one we're going to find at D, and at D we know that it's going to be compressive. Okay, the bending is going to be compressive. So the stress X. Oh, before I go on, I want you to look at this. Okay, this is the part that I need to elaborate. So remember, I told you guys to do what? Pick the datum from the top. Right? Pick the datum from the top. If we were to pick our datum from the bottom, what will happen? Okay, so I'm going to call this distance EB. Okay, EB is the bottom. So we know that EB, so over here you have EB is equal to 20 minus by 8.154. So when you calculate from the bottom, you get 11.846. Right? You calculate from the bottom. Okay, you're going to get 11.846. So let's say you don't want to listen to my advice. Okay, it's okay. My daughter also don't listen to me. It's fine. I understand. It's more difficult for my daughter not to listen to me because at the end of the day, I'm living under the same house as her. You don't live the okay. Okay, so I've got. Can we repeat the deformation pattern and directions of MZ? So the deformation pattern, I do apologize. Okay, you asked that question 11 minutes